Isaac Newton Institute for Mathematical Sciences. My name is Christy and I'm the Deputy Director. I'm delighted to say that our speaker today, Professor Edward Witten, has kindly agreed to put his trust in the hands of technology and is speaking to us here in Cambridge from his home institution, the Institute of Advanced Studies in Princeton. Before I formally introduce Professor Witten, let me tell you a little bit more about the Isaac Newton Institute and share with you a few formalities. Based in Cambridge, the Newton Institute is a national facility that supports mathematical research throughout the UK. It's funded by the Research Councils with contributions from the London Mathematical Society, the Leverhulme Trust and other charitable trusts, and of course with significant support from the University of Cambridge. This is a very special building, built as a creative space designed to nurture individual research and research collaboration.
Thanks very much for setting everything.
I should mention that there are over 140 square metres of blackboards in this building. Before we begin, a few practical matters. Firstly, please can I ask all of you in the audience here in Cambridge to ensure that your mobile phones are switched off. Even in standby mode, they interfere with our audio-visual system and will cause a buzzing sound that will be streamed live to the world and recorded for posterity. There will be no fire drill, so if the fire alarm sounds, please vacate the building and congregate in the car park. So finally, we are delighted that Professor Witten can join us today from Princeton and participate in one of our current programs on mathematics and applications of branes in string and M theory. Professor Witten has held positions in Harvard, Princeton and Caltech, and is currently Professor of Mathematical Physics at the Institute for Advanced Study. His awards and honours are far too many to list. They include a MacArthur Fellowship, the Poincaré Prize, the Einstein Medal, the Dirac Medal, and of course the Newton Medal. In 1990, he was the first physicist to be awarded a Fields Medal, and in 2004, Time magazine stated that he was widely thought to be the world's greatest living theoretical physicist. On that, over to you, Professor Witten. Thank you.
Well, thanks for the kind invitation and for the opportunity to give this lecture by video conference. I'm not usually seated during the lecture, but I couldn't see any good reason to stand at the video conference. So I'll be talking today about superstring perturbation theory, which is a topic that was much more popular 20 to 25 years ago than it is today. It was much more popular in the 1980s, and an awful lot was done. Most of the questions were answered, but a few nagging details remained, and they remain to this day. That's the reason that I've chosen to go back to the question to reconsider it. So first of all, one of the most important ingredients in string perturbation theory is modular invariance. The role of modular invariance was discovered 40 years ago by Joel Shapiro after Claude Lovelace had explained the special role of 26 dimensions. Modular invariance completely eliminates the ultraviolet region from string perturbation theory, and consequently there's no issue at all about ultraviolet divergences. So we will have nothing new to say about the ultraviolet today. Where the literature of the 1980s left some small unclarity concerns infrared questions. The general statement one wishes to establish is simply that the infrared behavior of superstring theory is the same as that of a field theory with the same low energy content. So a field theory with the same massless particles and low energy interactions should have the same infrared behavior as string theory. There are a few aspects of this that I want to reconsider. It's a question of details, since 98% of the work was done 25 years ago. I want to begin by giving a few examples of what I mean in saying that the infrared behavior of string theory is the same as that of the corresponding field theory. Let's consider a Feynman diagram. Perhaps the most primitive question about infrared behavior is to ask what happens when a single propagator goes on shell. In this Feynman diagram, I've indicated two propagators. The one labeled 1 is generic. The one labeled 2 has the property that when its momentum goes through, the neighboring propagators also automatically go on shell. Suppose our particles are massless, so the propagator is 1 over k squared. In d non-compact dimensions, Well, the worst infrared behavior is when the momentum goes to zero, and the infrared behavior when the momentum in a single propagator goes to zero is what I've written, the d-dimensional integral of 1 over k squared. That converges if d is bigger than 2. The infrared behavior is worse for special lines like the one labeled 2 in this picture, where when that line goes to zero momentum, two neighboring lines also go one shell, and then you get infrared divergences unless d is bigger than 4. All this has a close analog in string theory. So, first of all, a non-separating line that goes to zero momentum is analogous. I wish we could tell this thing to not. Oh, I definitely don't want it to restart. Restart later. First of all, a non-separating line that goes to zero momentum is analogous to a non-separating degeneration of a Riemann surface. So I've indicated with the red arrow a line which is shrinking to a narrow tube. That's the string theory version of a particle that propagates for a long proper time and is nearly on mass shell. Now, a degeneration of a Riemann surface, whether separating or not, can be described by an equation xy equals epsilon, where x and y are local parameters on the two sides of the degeneration, and epsilon narrows the narrowness of the neck, or by conformal transformation, the length of the tube that separates the two sides. The contribution of the massless particle propagating through the neck in closed string theory, for example, can be written as I have. You integrate d to epsilon, epsilon to the L naught minus 1, epsilon bar to the L naught bar minus 1, and then you do an integral over k. For massless particles, L naught and L naught bar are k squared over 2. Now, we can actually compare to field theory without doing the epsilon integral. It's more useful instead to introduce the analog of the Schringer parameter by writing epsilon as the exponential of something, where the real part of something, or minus the real part of something, is the Schringer parameter of field theory, and s is an angle. The imaginary part of the exponent is an angle. The integral over s gives a factor of 2 pi, and we're left with an integral over t, the Schringer parameter. In writing this integral, I indicated the upper limit, namely infinity, but I didn't indicate the lower limit, which is controlled by modular invariance. The upper limit is where infrared problems, or infrared singularities arise, and the lower limit is where there would be ultraviolet problems. There are no ultraviolet problems because the lower limit is shifted away from zero in string theory, but there are the same infrared issues as in field theory because the upper limit at infinity is the same whether we're doing field theory or string theory. What we have at the bottom, in the last equation of this page, is the same as we would have in field theory, even before doing the k or t integrals, if we bear in mind the Schringer representation of a Feynman propagator. So field theory and string theory match without doing any integrals. Now, just as in field theory, we could also consider a situation where one momentum going to zero, one momentum going to zero causes other adjacent propagators to go one shell. That was the line that was labeled 2 in my picture of the multi-loop Feynman diagram. This gives an infrared divergence in 4 dimensions or less, whether in field theory or in string theory, and the issues are exactly the same. There are many other questions that match in a straightforward way between string theory and field theory. For example, cutting a diagram to probe arbitrarity, there you cut more than one line, putting more than one line in one shell, or in string theory, letting more than one line degenerate. Let's move on to the case where the match is a little less straightforward. This has to do with the separating line, meaning a single line in the Feynman diagram, or an internal line, where cutting that line decomposes the diagram into two pieces. I've drawn two cases in field theory, where in either case, the line which is labeled by the red arrow has the property that if we cut it, the diagram is decomposed into two pieces. The difference is that in the second case, the external particles are all on the same side of the separating line. Now, in either of these cases, we do not integrate over the momentum that passes through the separating line. It's determined by momentum conservation, and is simply the sum over all momentum entering on the left of the separating line. On the left, this momentum is generically non-zero, so for typical external momentum, we do not signal the one-over k-squared singularity. When we vary the external momentum, the 1 over k-squared gives a pole in the S matrix, at least in this approximation. This is physically sensible, and we do not try to get rid of it. On the right, things are different. The momentum passing through the indicated line is 0, and hence we will get 1 over 0 unless the matrix element on the line right vanishes. So a field theory with a massless scalar has a sensible perturbation expansion only if the tadpole or one-point function of the scale vanishes. So what I've drawn on the left here in blue is a single massless scalar that couples to that blob, which represents symbolically all Feynman diagrams, by means of which a single scalar can disappear into the vacuum. What is on the right is meant to be the number 0, not a moment of Feynman diagram. So we have to impose this condition that the blob vanishes for all massless scalars, although it's non-trivial only for massless scalars that are invariant under all the relevant symmetries, local and global. In field theory, if the tadpoles do vanish, we just throw away the corresponding diagrams and evaluate the S matrix by summing the others. So for a 4-particle S matrix I've symbolically indicated here, the class of diagrams we throw away. All diagrams where a single scalar is disappearing into the vacuum through an arbitrary blob. All this is relevant to perturbative string theory, since when we do have a perturbative string theory, there's always at least one massless neutral scalar field that might have a tadpole, namely the delta, whose existence, well, it controls the string coupling constant, and it's the reason that we do have a perturbative expansion with a coupling that could be small. So perturbative string theory will only make sense if the dilettante tadpole vanishes, along with other tadpoles if there are more massless scalars. In either field theory or string theory, the usual way to show vanishing of the tadpole of a massless scalar that's neutral under all symmetries is to use supersymmetry. Indeed, without supersymmetry, it's unnatural to have a massless neutral scalar in the first place. So supersymmetry tends to be an ingredient in any argument that the tadpole of such a scalar vanishes. Just as in field theory, we can distinguish different kinds of diagrams with separating generations. The red dots here represent positions of external vertex operators for external particles, and the red arrow points to a degenerating line. It points to a narrow tube where a Feynman diagram is, the tube is shrinking, that represents an on-shell particle in propagating through the narrow neck. It's the analog of the separating line in a Feynman diagram. And just as in field theory, the dangerous case is the one on the right, where all external particles couple to the same side of the Feynman diagram. As one should anticipate from what I've said, it's the picture on the right that causes trouble. And there are two reasons that this problem is harder to deal with than in field theory. The first is that technically, it's harder to understand space-time supersymmetry in string theory than in field theory, and to use it to show that the integrated massless tadpoles vanish. The second reason that the problem is trickier in field theory than in string theory is that string theory is more unified. In field theory, the tadpoles are the contributions of certain diagrams, and if they vanish, one just throws those diagrams away. String theory is more subtle because the tadpole is part of the diagram that also has non-zero contributions. For example, in oriented closed string theory, which I've used for all my pictures, there's only one G-lib diagram. It has the tadpole, but it has everything else. So we can't just throw that diagram away. We have to throw away the part of it that would have generated the tadpole. Vanishing tadpoles makes the diagrams of string perturbation theory inferent convergent, but only conditionally so. And so there's still some work to do to define them properly. This is actually one of the areas where one can slightly improve what was done in the 80s, but I won't be talking about that today. Instead, I'll be talking about the first point of using space-time supersymmetry to show that the tadpoles vanish. Since we can only hope for the tadpoles to vanish in the supersymmetric case, we have to do supersymmetric string theory. This means that our Riemann surfaces are really super Riemann surfaces. A super Riemann surface is a rather subtle sort of thing. It takes practice to get any intuition about them, and I can't really describe this topic today. Now, all I'll say is that a super-Riemann surface with n equals 1 supersymmetry is a supermanifold of dimension 1/1 that has some additional structure. And on this supermanifold, there are two kinds of vertex operators we consider: inverse Schwarz and Riemann vertex operators. An inverse Schwarz vertex operator is inserted anywhere on the super-Riemann surface, while a Riemann vertex operator is inserted at a point on which the superconformal structure
Sorry, Edward, we've lost sound for a minute. Just 1 minute, please. Steve? Sorry, just a minute, we've lost sound.
We've
lost sound.
Have you unmuted it?
Yeah, I've just unmuted it now to tell him. Yeah. We've lost sound. I didn't touch anything.
Can you wave if you can hear us? I can try redialing again.
1 moment, please.
Can you sign language it?
Was he on his own?
Might have been, I don't know. Yeah, I believe so. Only there was someone helping him.
This is the number. So I'll go and phone him in a second, but you want to keep trying 192 for the dot. Yeah. Just press start. 192.
We have a small technical hitch.
Explicitly depends on the metrics. And so therefore I don't, it also... Do you know the older patterns? Or have you ever seen anyone clarify?
Still trying to get it to work.
Good or not?
Broadcast there as well. He's trying to get the web broadcast. Broadcast. And Professor David Tong has volunteered to give a lecture in his plane. It's being recorded.
I guess the Don't you have a slide?
Edward's listening. Yeah, I mean, we can do something. Hopefully we'll get him back.
Feel like there's zero portion to probably don't want to.
No, zero torsion.
And then,
So, yeah, I mean, there's an explicit expression.
yeah,
Right out.
yeah.
Manifold flag.
Well, that depends on the user. So, yeah.
Yeah, they're just going back into the room their end, so they're going to both connect together.
Why did we just lose sound, Gen 2?
Don't know where the sound went.
View the previous slides.
Sometimes just define diagonal
Yeah, in some sense.
this is like
But the point is that there's engagement dimensions.
yeah, so omega is a connection. So
Well, I mean, it's given given the method, just many easy.
it's so
Yeah, yeah. But then,
but let me fix that. So let me fix the gauge.
I've just spoken to him. He said he was just going back into the room.
still get the same
Once you give me
You
a
have the same number of terms. Yeah, so have the same.
that's what I would have.
But then the spin connection has this one.
Well, you could have a cancel.
Oh, the screen. Steve? It's ringing, it says. Oh, there we go.
Hello.
Hello, sorry, we lost sound there, Edward.
Do you have the sound now?
Yes.
Okay, so where did you lose?
We have your we have your definition of a super Riemann matte surface, and that was where we got to. Yeah, we have your definition of a Riemann surface, super Riemann surface, and that's where we're up
What
to.
would you say is
Yeah,
spin
well-
connection?
Yeah, I don't know. I'm just thinking why.
I mean, if you squint, I can ignore that. That's like a
We've lost the audio.
lost everything.
Can you hear us? Yeah. I don't have a number for that room.
You're right, okay. Can you hear us, Edward? We can't hear you.
Can you wave if you can hear us?
We can't hear you still. It seems... Okay, we've got someone working on it. Give it a minute. Hopefully it'll work out. Sorry about this. Any clues, Steve?
There's nothing we can do apart from phone and reconnect. Yeah. Do the reconnect the connection.
Can you try speak again, see how it goes?
And that's probably too.
Yeah, that's what I was wondering as well. Yeah. Well, just let me find something.
We do.
Well, we try one more time.
Problems that's flat.
So that bit is complex.
It's just the attention matrix is something bench.
If we reconnect, he said, if we reconnect, we'll get the sound. Let's see how long it lasts. Let's try one more time, and if it doesn't, then we reconnect.
So that doesn't appear.
Jeff in the room. Are you on your own? Is Jeff with you?
Yeah, hi Jeff.
Hi Jeff. Can you cut the connection and phone us back, please?
Probably good. Because it was
Because chorus is flat. Here's bundles of trees.
I really express my concern.
So doesn't that then mean that
You keep telling us to restart.
Good. We can hear you.
Okay, you can hear now?
Yes.
all the questions were
Okay, I think maybe this is a good moment to stop for a question or two. If there are questions from the audience.
Any questions?
If there aren't questions, I'm going to take that to mean it's been incredibly crystal clear.
Yes.
So far, yes.
So remember,
I was just going to say, if you could pick it up from the super Riemann surface definition, then that would be helpful.
once again, it's not a definition. I'm not telling you the definition.
Okay.
The whole interesting definition is in the special structure, a superconformal structure. If you look,
so is there an example
There's
where
nothing we can do this end problem. Just keep trying to connect.
All right, what are we going to do? Try one last time? Then?
this
At some point, we're just wasting.
I mean, the torus might be a bad example because it's kind of.
it's a sort of degenerate. So.
It doesn't need. Don't need to do it. It would last.
One more then.
All right.
We're going to.
understand?
Yeah. We're going to try and go from here, and then if it cuts again, we'll just cancel it. I'm very sorry about this interruption. Okay.
So, as I just remarked, a Nevers-Schwarz vertex operator is inserted anywhere on the super Riemann surface, while a Ramon vertex operator is more subtle. It's inserted at a point at which the superconformal structure of sigma has a certain kind of singularity. So, Renan, Martinek, and Schenker in 1985 explained what sort of vertex operators are inserted at superconformal singularities.
I'm sorry, I've lost sound again.
It's gone. We have to end it.
I think it's been half an hour.
Yeah. I think we should call it a day, right? It's not working.
I don't think we can waste this time.
Yeah. To see if we can get him back to apologise.
I'm very sorry to all of you, and I apologise to all of you. We were assured, that everything was in order, and we had a hardware failure this morning, and things have spiralled down from that point. So I'm very, very sorry, and this should have been such an exciting occasion. We were all so thrilled that you were able to join us for Princeton.
Edward, can you hear me?
I hear you fine, yes.
It's cutting out too. It's cutting out too often. I really think it's not worth continuing because every 5 minutes, in fact, every minute we lose sound. So I think the best thing is, unfortunately, we're going to have to cancel now. I really apologise for this.
It's your fault.
we can try and continue, but I'm really worried that if this just continues every minute, then it's no good for you.
It's your call, okay.
Should we try one more time while it's going?
Can
You can
we
try, sure.
apologise in advance to you in case it drops again?
We'll try one more time,
That's fine.
and then if it cuts, I mean, it's just not working, and I don't know why. But
And I'm so sorry, we had a hardware failure this morning and we've been trying to write the problem since then and it's not turned out quite as we had hoped. And I'm so sincerely apologise.
Okay, don't worry about it, but we'll give one more try.
okay.
Give it another go.
Yeah.
Far away now, quickly while you've got time.
So, most practical calculations have been based on this work of Friedrich Mortnick and Scheger from 1985. But it left a few details, which we'd like to clarify. That's what we're aiming for today. Now, I think the main reason for whatever unclarity does surround this problem is that to understand it properly requires a little more sophistication about supermanifolds and integration over them than in most problems involving supersymmetry and supergravity. So some level order cases are deceptively simple and really don't give a good idea of a general algorithm. For example, in genus 1, the dilettante tadpole vanishes in OR10 by summing over spin structures. But the fact that this makes sense depends upon the fact that in genus 1, there are no fermionic moduli. As soon as there are odd moduli, there's no meaningful notion of two super-Riemann surfaces being the same but with different spin structures. In particular, in genus bigger than 1, it doesn't make sense to sum over the spin structures without integrating over the supermoduli. In genus 2, the Oker and Fong found a very beautiful way to integrate over fermionic moduli first, after which the sum over spin structures makes sense and could be used to show the vanishing of the dilettante tadpole, and then integrate over the bosonic moduli. Their calculation is currently the gold standard, but it's more or less clear that for generic G, their procedure has no analog, and the only natural operation is the combined integral over all bosonic and trigonometric. This was constructed in the 80s by various methods by adapting the analogous formulas for the bosonic. Compact supermanifold is a well-defined operation of an ordinary manifold.
I'm going to continue a bit. We'll follow the slides.
Integrate has singularities. That's true precisely because of the infrared effects we've been talking about. They're completely fundamental for the physical interpretation of string theory, so this non-compactness isn't just a technical detail. It's part of the reason the theory works. There are singularities when a super-Riemann surface degenerates, as indicated in this picture by the red line. So we have to deal with the non-compactness. But the starting point is that the non-compactness, which is the inferred region, is the only difficulty. In fact, the statement that moduli space can be compactified by adding only the divisors in this inferred region of this degenerating surface is a precise statement of the fact that for genus G there's no ultraviolet problem. Although supermoduli space is very subtle, if you ask precisely the questions as answers you need, these particular questions tend to have simple answers. For instance, although a sum over spin structures independent of integration over the supermoduli does not make sense in general, there's a very small piece of it that makes sense when a node develops. The node is just a name for the singularity indicated by the red line, where the Riemann surface is splitting into two, lovely separating into two branches. The fact that this small piece of the sum over spin structures makes sense in the infrared region leads to the GSO projection or the physical states that propagate through the node. So even though you cannot do a general sum over span structures without integrating over moduli, for a little bit of it you need to show that only GSO invariant states couple in scattering averages. In other words, they only look.
Okay, I say call again. I think we're actually making some progress through this, and he's being patient with it. So if you guys can bear to go with it, we're following a fair amount with the slides. If while we're reconnecting you want to make a tactical exit while he's not watching, you could do so. But let's reconnect again, Steve.
They're connecting to us.
Fantastic.
Hello?
Hi.
Yeah.
We're still
I
here.
hear you.
Yeah, we hear you.
Okay.
Keep on going.
So, did you follow?
Yep. We've got to the end of propagating through the node.
What do we do?
I don't think it's just a waste
I
of
don't
time.
think this is working. Sorry, Edward, we lost sound again.
He's on
Sorry.
the next slide. He's on the next slide, David.
Yeah, but we've lost sound. So
This is getting.
Could you call back, please?
Steve.
Yeah, I think we should call it quits.
Okay.
I mean, we're wasting his time.
Yeah,
and you're
no,
wasting
I
our time.
absolutely agree with that.
And I think
So-
there should be better standards in this institution.
I am so sorry. I all I can say is I really apologise.
Is it conceivable? Might it work better if you call us? Is that conceivable?
There'd be no difference.
Okay.
Yeah.
Shall we try to continue?
It's your call. We're very aware that it's your time that we're taking up. We do not wish to waste your time.
I'm okay for a bit. It's fine.
Okay.
Well, if he's willing to bear with it, but. But if you're willing to continue in this way, we'd be very happy to hear the rest of the talk, or as much as we
I'll
can.
continue and I'm going to cut down on some digressions, just for practicalities. So this page is devoted to another thing that actually does work, which is that the description of the moduli space in the infrared region is as simple as it is for a bosonic Riemann surface. In the few sentences written here, I've given a very brief technical explanation of how that's true, although to understand it better is a longer story. But without going into any details, let me just say that although supermoduli space is quite complicated in general, its infrared region is quite in parallel with what it is for bosonic strings. That's a fact that really wasn't adequately used in the literature of the 80s. It's actually the fundamental reason there's no integration ambiguity in superstring theory. Those of you who were in the field in the late 80s may remember people talking about an integration ambiguity. There's no integration ambiguity because the Deligne monthly convectification tells you what a good parameter is at infinity. Not exactly enough, but with enough precision so that there's no integration ambiguity. So it's impossible to explain everything today, and I decided to explain the origin of the picture-changing phenomenon. So for this, we're going to start with an ordinary manifold M with bosonic coordinates T1 up to Tn. For each of the T's, we integrate the corresponding fermionic variable dt, which we consider to have degree 1. Then we consider a general function f that depends on the t's and dt's. But since the dt's are fermionic, f inevitably can be expanded as a polynomial of the dt's. For example, I've written a term that has an order p of dt's, so we call it of degree p. It's usually called a p form. And then we define an operator, t, which is the sum of dt times the derivative with respect to t, that amounts p forms to p plus 1 forms. And over such functions, we define integration by following ordinary rules to integrate over bosons and fermions. So the simple curly d of t and dt is just a variance integral over the t's and dt's. So you could open a math book and read about integration of a differential form, but if you're comfortable with the integral over bosons and fermions, that's all that it is. The rules of variance integration tell us that the integral over the dt's is non-zero only if all dt's are present in f. So when we expand f in a polynomial of the dt's, the only term with a non-zero integral is the one that's proportional to all the dt's. So if n is n-dimensional, a p form can be integrated only if p equals n. Another important fact is that, as I've stressed, f is automatically a polynomial of dt's. And then we've got Stokes' theorem that if n has no boundary, says that if f is d of something, then its integral vanishes. So this story has an analog for supermanifolds with only one or two changes. But the change leads to the picture change, the phenomenon of the picture number. Suppose M is a supermanifold with even and odd coordinates t and theta. We imitate the bosonic case, so we add new variables dt and d theta, such that for any even or odd variable x, dx has opposite statistics from x. We define a scaling under which dt and d theta have degree 1, while t and theta have degree 0. And then we define the exterior derivative in the obvious way. It's a sum of dx times the derivative with respect to x. It increases the degree by 1. By a form, we mean a function of all these even and odd variables. But unlike the previous case, a form is not automatically polynomial in all the dx's, because some of the dx's are orthogonal. If it's polynomial in the dx's, but in that case, f can't be integrated. We'd like to define an integral over all the x's and dx's, where x is any of the t's and thetas, and dx is the corresponding dx. But if f has a polynomial dependence on the even variables d theta, the integral over those variables will certainly diverge, since a bosonic integral of a polynomial doesn't converge. A typical example of what can be integrated is the form I've written, which is proportional to all the dt's, but they're delta functions of the d thetas. It's a form because it's a function of the x's and the x's. What is called an integral form because it can be integrated. The integral over the d thetas is 1 because of the delta functions. The integral over the dt's is also 1. Well, the integral over the d thetas and the dt's is 1, and setting to 0 all the d thetas and dt's which are in f. So you can integrate out the dt's and the d thetas with the help of the factors I've written, the dt's and the delta of d thetas, and you're left with an integral over the t's and thetas with no dt's and d thetas, and the integral on the right-hand side is the ordinary Beresford integral. So this is the right framework for generalizing differential forms to supermanifolds in such a way that you can integrate. So more generally, if you want to integrate f of x and dx not over m, but over a submanifold m, whose bosonic dimension is p and its fermionic dimension is q, then f must obey two conditions. Its degree must be p minus q, and its picture number must be minus q. The picture number is defined as the number of d thetas with respect to which f of x and dx has delta function localization. So delta function localization doesn't mean just delta of dx. We also know delta prime of dx or delta double prime of dx. Delta function localization means distributional support where d theta is 0. So the picture number is minus the number of d thetas where you have this distributional support. And the degree is p minus q. So it's p minus q, not p plus q, because fermions have opposite transformation to bosons. dt has degree 1, but delta d theta has degree minus 1. So our basic example of a form that can be integrated has a degree which is the number of bosons minus the number of fermions. And that generalizes to the fact that what can be integrated has to have degree p minus q, as well as picture number minus q. I wish the picture number was plus q, but the way that Frey and Martinek and Schenker define the picture number, it unfortunately is minus q. The next topic I want to discuss is integration by parts. We need integration by parts to prove decoupling of pure gauge degrees of freedom, and also to prove space-time supersymmetry and vanishing of tadpoles. Integration by parts is one place where what was done in the 80s can be improved. Traditionally, integration by parts were arguments were made by first integrating over odd moduli and then using the ordinary version of Stokes' theorem. What this introduces to the technicalities and complications for which the literature of the late 80s was notorious. There's a perfectly good superanalogue of Stokes' theorem, and we're better off using this. You probably all know the basic idea of fermionic integration by parts, which is that for an odd variable alpha in any function f of alpha, the integral of a total derivative of f vanishes. That's how Berezin discovered the Berezin integral. He wanted to make that true. Integration of forms over supermanifolds has an equivalent relation which says the same thing that you would suspect from ordinary integration by parts. It says what I've written. The integral of d lambda over x is the integral of lambda over the boundary. Here, lambda and d lambda are integral forms with delta function localization with respect to all d thetas. So you can make this formulation work for superstring perturbation theory, and in particular, a scattering amplitude of particles, n particles, given by vertex operators, v1 up to dn, is associated with a volume form, upsilon, that has to be integrated over supermoduli in this case. Just as for the bosonic string, if one of the vertex operators is a BRST commutator, then the volume form upsilon is exact. And then in checking the decoupling of Q with W, the BRST commutator, the left-hand side is given by the integral of an exact form, which by Stokes' theorem is a boundary integral. So if lambda has a good behavior on the boundary, then the right-hand side vanishes, and so does the left-hand side. So this is the strategy.
Should I wave and pause him?
Yeah. Sorry, Edward, we've lost sound again.
Yeah, we lost sound again.
Neil, can you put the mic on so that you
It is
can hear
on,
us
it
saying
is
that?
on.
Okay. It is on.
Yeah, we've lost sound again, I'm sorry.
Right, well that lasted for probably about 10 minutes that time, so let's try calling back again and see if we can keep going to the end. If you're all happy with this, we should get there.
All right.
Yep, there is.
He was annoyed.
He was annoyed. He expressed that.
Yeah, that's true.
Hello again.
Yeah.
Yes.
Great.
So the last thing I said was that the super version of Stokes' theorem enables you to understand gauge invariance the same way you would understand it for the bosonic string. With only one difference, that it makes sense, because there are no tadpoles or incremental divergences. So that argument is much simpler than any argument using the bosonic version of Stokes' theorem. It also has an important corollary. If you know that the massless tadpoles vanish, then space-time supersymmetry is a special case of the vanishing decoupling of pure gauge modes. You may deduce this from the following standard argument, which you all really should know from your field theory courses. You take a scattering amplitude involving a soft gravitino. So
Okay, I think, yeah, we can hear now.
if you can hear me again,
Yeah, thank
the
you.
last thing I said was that even if you don't follow all the details, what I'm telling you is that if you use the right supermanifold version of Stokes' theorem, that the structure of superstrings is quite parallel to the structure of bosonic strings, where you prove gauge invariance to decoupling of pure gauge modes using Stokes' theorem. Space-time supersymmetry is a corollary of an argument that you may know from your studies of field theory. So you consider a scattering amplitude involving a gravitino of momentum k with a polarization vector spinor eta. Can you still hear?
Yes.
Yes.
So a matrix element for emission of a soft gravitino has various singular terms where the gravitino attaches to an external leg. I've drawn the picture to that there is an equivalent string theory picture that involves a narrow neck rather than an external line. So the line that emits the gravitino or absorbs the gravitino is just slightly off shell. So its propagator is singular. I've computed here that the propagator of this line is minus 1 over 2p dot k, which is singular as k goes to 0. As well as the denominator, there's also a numerator, which involves a matrix element of the supercurrents. So the contribution of this particular singular line has a numerator that we know from supersymmetry and a singular denominator that we also know from Feynman kinematics. Now, if the gravitino vector spinor eta is longitudinal, if it's k, the momentum times something, the whole amplitude must vanish. That's a special case of the decoupling of pure gauge modes. It's hard to evaluate this condition exactly, but its leading behavior as k goes to 0 is a sum of the singular terms that we've discussed.
Okay.
Okay, what proportion are we through?
I don't know.
Do you know how many slides, where we're on, how many out of how many?
Yeah, 43 or 54.
Okay, so we're making progress.
I think we can do this lecture in 5 or 10 minute installments, but not in 30-second installments. It's too hard to know what you've heard.
Yeah.
We heard everything up until the last 5 seconds. So
Okay. So what I said is that the word identity is complicated in general, but as k goes to 0, it becomes simple. You get a sum of the singular terms I've described, and the sum of those terms must vanish, and that's the word identity of space-time supersymmetry. So you may know this type of argument from field theory.
Okay, I think that's it. It's connecting with your instinct. If we get 5-minute chunks, it's working. If it's 30-second chunks, okay. He's persisting. You'll call.
You know, what I've written on these slides is so detailed that I almost wonder if you should just read through them and then ask me questions at the end. But as long as the sound persists. So the argument I've given is the same in field theory or string theory, but in both cases I've left out something so far. The supersymmetric word identity can contain another term if the coupling of a soft gravitino has a singular contribution that I've indicated here, where psi, the gravitino, through a blob, the red blob, couples to a massless, previously massless fermion, lambda or psi, where lambda has been half, and psi is the gravitino group. This happens if Loops generated term of the effective action is going to give psi a mass term, either a psi bar psi term or a psi bar lambda term, where lambda is a previously massless fermion. In the first case, supersymmetry is spontaneous equality, where lambda is a Goldstein fermion. In the second case, we landed inside a superspace with unbroken supersymmetry. An example of the first type is known in literature. No example of the second type seems to be known. In many classes of string vacuum, it's straightforward to prove that this doesn't happen. For example, in all of the 10-dimensional superstring theories, this doesn't happen for rather trivial reasons of quantum numbers. And there are similar arguments in most compactifications to 4 dimensions. So all we need in order to land in a happy place is an extension of this kind of reasoning to show that the massless tadpoles vanish. follow from space-time supersymmetry, I believe that the type of argument I've given is not quite powerful enough to prove it. But from the experience with the old lecture, we know what we have to do. We have to make the same kind of argument with k set to 0 at the beginning. We use the fact that the vector vertex operator v psi k of a graph theta of polarization longitudinal proportional to k is q of something. So if k was 0, then v was 0, and the relation is that 0 is q anti-commutative with s, where s, which is the limit of w as k goes to 0, is the fundamental spin field. S has ghost number 1, while a vertex operator for particle emission such as v has ghost number 2. So by analogy with more simple cases, the condition that q with s is 0 should mean that s generates a symmetry in spacetime. For practice, let's look at a correlation function of s with any number of other vertex operators. It can't be integrated over moduli space gamma because the ghost number is too small by 1, since s had ghost number 1 instead of 2. But it can be integrated over the boundary of moduli space. And that integral is 0 because q with s is 0. So if something is 0, namely the integral over s times the product of other things over the boundary of moduli space. This relation can be written as a sum of contributions from the many components of the boundary of moduli space. Many of them don't contribute because the momentum formative node is off-shelf.
Okay, I think we take the suggestion and we keep reading through slides, and then we ask questions at the end.
I think we've only got 2 slides left.
Exactly. Therefore,
I think there's 2 more. Maybe that's the last slide. So.
Almost at the end.
Yeah.
Very good.
We're almost finished, so I think we should persevere.
Yeah.
Thank you.
So I've written here some contributions which do contribute. S has momentum 0, V is on shell, so S plus V has the same momentum as V, so it's certainly on shell, and therefore it does contribute. Now these are the only non-zero boundary contributions. Finally address the question of whether there's a massless tadpole, we replace the product of n vertex operators with a single vertex operator d lambda of a massless variant with a superpartner of a scalar phi whose tadpole we want to understand. The relation at 0 is the integral of the modulus, boundary moduli space of s times v lambda is now simple because the boundary of moduli space has only 2 types of components. 2 types of components are distinguished by whether s is on the same side as v or not. So, the first term here is the delta on tadpole. S times v equal to phi, the scalar on the same supermodel as lambda. And then phi disappears into the vacuum, or the G is G surface. That's the G is G contribution to the tadpole. The second contribution is non-zero precisely when supersymmetry is spontaneously broken or cosmological constant is generated. So the relation I've written here is the one we want, that if supersymmetry is valid, it's not broken, and we land in
This is the last slide.
we're essentially
Yeah.
This very beautiful picture, I think, is the right way to explain that the massless tadpoles vanish. And it's very important that it includes a second term. The attempted derivations in the 80s were much more complicated, but they also didn't see in an equally clear way the second term, because physical interpretation is that what we're trying to prove is only true if there's no Boltzmann fermion and we're not generating a cosmological constant. So when one can show that the gravitino can't generate a mass in perturbation theory, for instance in Arcan, this relation should remove the very slight unclarity that is around the superstring perturbation theory. And now I thank you as well for your patience, and I'd love to entertain a few questions.
Questions?
I had one. So are you it's definitely relying heavily on the supersymmetry? Would you go so far as to suggest that indeed this claim that string theory requires space-time supersymmetry is true?
Perturbative string theory requires space-time supersymmetry. Let's clarify what that means. First, perturbative string theory requires a variable coupling constant. First of all, in general, string theory has no dimensionless parameters. Perturbation theory in general requires an adjustable coupling constant. But string theory has no adjustable parameters. So the only way to have an adjustable coupling constant is that the adjustable coupling constant is the value of the field. So there's only an adjustable coupling constant when there's a massless field. This vacuum excitation value is undetermined in perturbation theory. But if that's true, there's a question of the tadpole. Is it true that quantum fractions generate no tadpole for that field? Otherwise, perturbation theory can't work.
Sorry, we've lost the sound again.
Okay,
we've lost it
is there
again.
anyone else who's going to have another question? Are there going to be any other questions?
Sorry, Edward, we just lost the sound just at the very end there. And I think the thing to do, because we've got these problems, is we'll probably end it here. And thank you very, very much
Yes.
for your patience.
Thank you.
Thank you very much. Bye-bye.